Thank you so much, everyone, for being here for my talk, and also for the organizers and session chairs for organizing this extremely interesting and wonderful conference. I've enjoyed going to Stony Brook for several years now, and so really honored and privileged to be part of the lineup this year. What I'm going to be talking about today is simple and approximately optimal contracts for payment for ecosystem services. And this is joint work with my student Wanyi at Stanford, as well as Itai Ashlagi. Great. So today I'm going to be talking about payment for ecosystem services. And for those of you who haven't heard of this, essentially what we're doing here is we're going to pay owners of natural assets for their ecosystem services of conserving those assets. So think owners of forest land or watersheds, and either not cutting down trees or doing things to keep the water pure. And so these kinds of payment for ecosystem services, or PES programs, have been growing in popularity all over the world. And so here I'm just showing you some of the PES programs that are occurring in Mexico, the United States, and China. And a lot of these are part of a wider United Nations REDD+ program. One prominent example that I want to highlight is a recent RCT that was conducted in Uganda by Jayachandran et al. And they showed that in this RCT that one particular PES program reduced deforestation by 50%. And so especially in these developing world settings where there are lots of smallholder farmers who really rely on their natural assets for supporting their livelihoods, it is possible for PES programs to have a significant impact. However, overall, the empirical findings on PES for forest conservation are pretty mixed. And so this 50% is sort of on the upper end of the spectrum, but we find anything from a 50% reduction in deforestation to no impact at all. And so the goal of my talk today is to think about using a contract design approach, a contract theory approach, to explain when are PES contracts effective and when might they not be. So one thing we can immediately do when we look at these programs from a contract theory perspective is we notice the structure of the contracts. The vast majority of PES programs use what we're calling conditional contracts. And we call them this because they have what in these in this literature is called a conditionality requirement, which is that forest owners are paid conditional on conserving all of their forest. So you're paid if you conserve all of your forest, and if you cut down anything, you're not paid at all. So of course, this is just one kind of contract, right? We could also pay for intermediate levels of conservation. And so rephrasing our original question, we can ask, when are conditional contracts effective for PES? And can we improve on PES outcomes by using other kinds of better designed contracts? Great. So just as an overview for where we're going today, first, I'm going to introduce this principal agent model, where we consider the principal being the government or NGO that is paying the smallholder farmers for their ecosystem services, and the agents are those farmers who are being paid to not cut down trees. Given this model, we can very simply characterize the optimal contract and start asking about the performance of simple contracts. And I'll show you about some of these. And finally, we take our theoretical findings and we perform some numerical studies using US land use data that allow us to illustrate how our theoretical findings could be useful when thinking about designing PES programs in practice. A quick slide on related literature. So there's a lot of related literature. I'm not going to have time to get into all of it today, but just wanted to highlight that there's this rich literature on PES. A lot of these studies are empirical, and so there are lots of very nice surveys on them. But what we're going to primarily draw on today is this paper, 2013 paper by Mason and Plantinga, where they put forth the model that we're going to be using. In addition, our paper also has connections to the contract design literature. And so in particular, we take a robust contracting approach that has been growing in use in the economics, operations, and computer science literature. So with that, let me jump right into the model. And as I mentioned before, this model is based, essentially taken from the Mason and Plantinga paper in 2013. We're going to take a principal agent model. Here our agent is the smallholder farmer who is being paid to conserve their land. And we're going to assume that they have an observable amount of initial forest area, may not. And so you can think of this as maybe the government knows which parcels of land belong to which farmers. They can also observe through satellite imagery how much forest area is originally on those parcels of land. And so we're just going to assume that the initial forest belonging to the agent is known by the principal. And so this also allows us to just think of one principal, one agent, also allows us to normalize this initial forest area to whatever we want. So for the rest of the talk, I'm going to think of this forest area as just one. But what's unobservable to the principal is the agent's baseline conservation. Okay, so this is the amount of forest data that they would conserve in the absence of any incentives if there were no PES program at all. And so this data is going to be distributed between 0, which is not conserving any of the original forest area, or 1, conserving all of it. And the principal only knows the distribution of this conservation. And so now what the principal can do is pay the agent to take different conservation actions. Suppose the agent takes some conservation A, it's between 0 and the original amount, A naught, then their conservation cost is going to be flat at 0 up until their original baseline conservation. And then it's going to be increasing and convex beyond that point. And so one way you can think of this is the conservation cost is capturing the opportunity cost of the land. What else could the agent do with the land if they were not conserving it, if they were allowed to cut it down? And so maybe you're thinking of a smallholder farmer, their alternative use for the land would be to develop it for agricultural purposes. And so there, likely what the farmer would do is first conserve the least agriculturally useful parts of forest land. And as they're conserving more and more, they have to draw on more and more profitable agricultural land. And so that's why their conservation cost is convex. Okay, and so as I mentioned before, the agent, the principal can pay the agent to take conservation actions. And so the agent's utility is just going to be linear payment minus cost of conservation. Great, that's the agent. Moving now to the principal. The principal is going to have some environmental value of K dollars per unit of area forest. And so a little asterisk here, just noting that we are making an assumption here that forest benefit is linear, and this is a non-trivial ecological assumption. So let's say we're thinking about something like carbon sequestration. Then this linear approach is pretty reasonable because the amount of carbon that would be sequestered by forest is proportional to the volume of forest. But let's say we were interested in something else like biodiversity. Then we really care about complementarities. We care that the forest land is close to each other. And so this linear benefit of forest is not able to capture those complementarities between units of land. You can think of this environmental value K as the social cost of carbon. So what is the value to the social planner for having this land? Okay. And so now what the principal is going to do is select a contract that pays the agent some price P A to conserve forest amount A. And their objective is to maximize their environmental value for the conserved land net payments. Okay. And then we put in all the usual constraints. We want it to be incentive compatible. We want it to be individually rational and limited liability. So you can only pay agents positive amounts. You can't charge them or tax them. And so given this setup, the optimal contract is very simple. You can take standard contracting approach, the classical solution with a little sort of tweak that we have this boundary condition that the amount that can be conserved is between the lower bound of 0 and the upper bound of the initial forest area. But otherwise, everything looks like the same, and we can take the direct revelation contract approach, where for each agent type theta, we say, here's your payment P theta, here's your amount you're going to conserve for A theta, and we put in, we're maximizing the amount conserved, net payments, subject to incentive compatibility. The utility for an agent of type theta who takes the action for a type theta is better than if they take some other action. Individual rationality, their utility is going to be non-negative, and limited liability, their payment is going to be non-negative. Okay, standard. And just to give you a sense of what that contract looks like, here's an example for where that baseline conservation distribution is uniform. So all I know is my agent is they're like the amount they're going to conserve without the contract is uniformly distributed between 0 and 1, and I get something that looks like this. The takeaway you should have from this picture is on the left, I'm showing you how much you pay the agent. On the right, I'm showing how much they'll conserve. And really what we're taking away from here is that these NGOs that are implementing these contracts will look at this and say, this is way too complicated, right? Let's say we wanted to implement this contract, we would need a menu with an infinite number of options to be able to capture this non-linearity, this convex region over here. And so, we're talking to these NGOs, they say even a menu with, 5 options, 10 options is too complicated. And so this optimal contract is probably not usable. So what we ask is, what can we do aside from the optimal contract? Can we use simple contracts to still attain a good proportion of the performance of the optimal contract? So what I'll do now is I'm going to look at just 2 kinds of simple contracts. The first is the conditional contract that is used in the vast majority of these programs. And just as a reminder, in the conditional contract, you pay proportional to conserved forest area if and only if the agent conserves everything. Okay, there's no deforestation allowed. On top of that, we also consider what we call linear contracts. And so here we just get rid of the conditionality condition. So we're going to pay an amount that's proportional to your conserved forest area and just however much you conserved. You don't have to conserve all of it. In the paper, we also consider what we call conditional linear contracts. And so again, paying proportional, but only if the conserved amount exceeds some pre-specified threshold. So you have to conserve at least 50% of your enrolled land. And the performance measure we're going to use is this approximation ratio. So this is the percentage of the optimal contract payoff that is achieved by the simple contract. So the objective achieved by simple divided by the objective achieved by opt. Okay, so jumping into the results. First, looking at conditional contracts. Again, here we're paying proportional to conserved forest area if and only if there's no deforestation. And so what you're optimizing here is what is my price P that I'm going to pay per unit area. And so if we optimize this price P, we find sort of 3 regions that characterize the performance of these conditional contracts. And these regions are parameterized by this K over H. And so a reminder, the K is the environmental value of the land to the principal. The H is in the agent's conservation cost. And so you can think of that as the value of the land to the agent. Or alternatively, you can think of this as the environmental value of the land relative to the agricultural value of the land. Okay. And so when K over H is large, that means the environmental value is really high, then the best conditional contract is the optimal contract. And why is this? Well, the environmental value is high enough that the principal is willing to pay a lot of money, and they pay a lot, and then the agent conserves everything. So that's great. When K over H is small, what we see is that the best conditional contract is no contract at all. Okay, the value is too small. It's not worth it to the principal to pay anything to the agent. And so the price is 0, and the agent just conserves the amount they would have conserved in the absence of the program. Now, where things are really interesting is in this intermediate region. And so in the paper, we characterize the thresholds, and we also look at what happens in between these thresholds. And what we find is that the best conditional contract can perform arbitrarily poorly. It can get 0% of the optimal contract payoff. Okay, so just to give some intuition for why this is happening, let's think about this super simple example. All I have is one agent. There's no information asymmetry. The principal knows that the agent, in the absence of the contract, would prefer to conserve nothing. Okay, without the contract, the principal is just going to cut down all of their forest. Okay. And so in this setting, the best conditional contract will really, the only things I can do are either here on the left, I'm paying the agent to conserve everything. Okay, I'm paying them just enough so they're willing to conserve everything. And if that is too costly, then I don't pay them and they don't conserve anything. Okay, and so if I do this, this is my payoff. My payoff is either k minus h over 2 or 0, the better of those. Now, what the optimal contract does is it pays the agent to conserve an intermediate amount. And what is the intermediate amount? It's a k over h. So there's a relative environmental value. And when we do that, I'm not going to go through the whole calculation, but you get this sort of k squared over 2h as your objective. And so you can see if I set k to be small enough, so k over h is less than or equal to 1/2, then on the top here, I'm going to pick 0. But on the bottom, for the optimal contract, I get non-zero payoff. So the conditional contract is performing arbitrarily poorly. And why this is happening is because the conditionality restriction is too strong. It's really binding the agent. It's saying you have to conserve everything. And then to incentivize them to conserve everything, the principal has to pay a lot more than is optimal. And so what can we do about this? Moving on now to the linear contracts, what we're going to do is just going to relax that conditionality condition. Okay, you don't have to conserve everything. If you conserve partially, we'll pay you partially. And let's see what happens if we now set the optimal price, given that we have a linear contract without a conditionality restriction. And so what we find here is a very nice result that for any k, so any environmental value, for any h, so this is any conservation cost for the agent, and any f, this is distribution of their baseline conservation, there's a linear contract where the principal pays a linear price, that's just the environmental value divided by 2. And this linear contract always guarantees at least half the payoff of the optimal contract. Okay, so immediately we see from this that the best linear contract is always able to achieve this constant factor of the optimal contract. And this is in direct contrast to the conditional contract, which can get 0%. Just to rephrase this a little bit, what we've shown is that there's this distribution-free linear contract. I don't need to know anything about the agent. All I need to know is the principles in my environmental value. And this contract will guarantee half the payoff of the optimal contract. Okay, and so just to summarize those takeaways, we looked at conditional contracts versus linear contracts. We looked at these 3 regimes for the relative environmental value. We found that when the environmental value is low, both of the contracts are the same. It's not worth it to pay the agents anything. And so there's no conservation. We have, again, the thresholds in the paper. When relative environmental value is high, we found that the conditional contract was optimal. And this is because in the conditional contract, you're able to pay the agent fully to conserve fully. Whereas the optimal linear contract is at most the same as the conditional. It can do worse. And that's because you don't have this conditionality. And so the agent can opt to conserve less than is optimal for the agent, for the principal. And then finally, in this intermediate region, the conditional contract can perform arbitrarily poorly, getting 0% of the optimal payoff, but the linear contract always achieves at least half the optimal payoff. And in fact, this is true across all the different values of k over h. Linear contract always gets at least half the optimal payoff, but this intermediate region is sort of where this is interesting, because this is the region where the conditional contract is not doing well.
So a quick question. It would seem that the principal may not know H often. He may,
Yes.
he knows K, but he may not know H, which is quite
Yeah.
uncertain. then
yeah, that's a really good question. So why don't I show you some of the data where there have been estimates of H. This gives us some sense of where these different PES programs are could be. And then, yeah, I think one thing that we find from our paper is that this relative environmental value is really important, right? If H is really high, then you're probably somewhere here. And so the linear contract is likely to do better than the conditional contract. Whereas if your H is low, then you're more likely to be here. And so then what's currently being used could perform very well. And so something we're sort of calling for is in the next section, I'll show you some of our simulations based on existing empirical work trying to estimate this H. And we're saying, you know, knowing this H is really important for the design of these PES programs. Great. So let me go ahead and show you what we did with that data. So just putting this little table here as a reminder and moving on to our numerical study. So here in our numerical study, what we're doing is we're using empirically calibrated data from this paper, the Mason and Plantinga 2013 paper. And so in this paper, they empirically calibrated the baseline conservation distribution, as well as the conservation cost for over 140 regions across the US. And in the regions, they also split them into low deforestation risk and high deforestation risk, sort of 4 different levels of deforestation risk areas, depending on how productive the land is for agricultural use. And so what I'm going to do is show you just one of those regions. I'm going to show you just Montana. And this is the low deforestation risk region. And so by that, I mean that the expected value of the theta, how much they're going to conserve, is large. Okay. So without the program, they would have conserved a lot. And so looking here, I have in the blue, the performance. Oh, and first on the y-axis, this is the percentage of the optimal contract payoff. And so everything is normalized with respect to the optimal contract. And I'm looking at different environmental values. I've plotted here the performance of the conditional contract, the best conditional contract, the best linear contract, the baseline contract where there is no program, and highlighted in gray when linear is doing better than conditional. Okay, so this is low deforestation risk. And in this region, we can see what we found theoretically, that for a high environmental value, the conditional contract is optimal. And for this intermediate region, the linear is always doing better than 50%. And because the conditional is going below the linear can actually improve here. Okay, but this plot is not very interesting, right? The region and the amount that the linear can improve on the conditional is very small. But what if we move to a region with high deforestation risk? So we look at when the expected deforestation or the expected conservation, expected theta, is small in the absence of the program. Now you can see basically what happened is the gray part got a lot bigger and the conditional contract is doing a lot worse. For best conditional contract over here for environmental value of about 250 is down almost to 30% of the optimal contract payoff, whereas the linear always stays above the 50% line.
Irene, 5 minutes.
Okay. Thank you very much. Great. And so sort of calibrating this to what would be useful for the programs. Let's say first we take the K to be the social cost of carbon. Okay, so this is estimated to be $58 per ton of carbon. And so, just kind of normalizing to the parameters that we use in the Mason and Plantinga paper, this corresponds to a K of 100. And so when we do that, we see we're in the blue region, or the blue dotted line, where for the low deforestation risk, the linear and conditional contracts are performing pretty similarly, but for the high deforestation risk, there's much more of a gap between conditional and linear. So we did this for US because we have this very detailed US land use data that's at the parcel level and that is able to estimate, in particular, the baseline conservation distribution, as well as the conservation cost. And we don't really have access to this kind of data for other countries in which the PS programs are being run. But let's say we do some back of the envelope calculations. Okay, we sort of look at the value of agricultural land in Brazil relative to the value of agricultural land in the US. And we also consider the areas where PES programs are typically run, which is in these high deforestation risk regions. Then we can see that there, the conservation cost H is halving. And so what happens when the conservation cost H halves is that K over H doubles. Okay, so what I've done here is I've doubled my K to reflect that K over H is doubling. And now I'm at this line, K over K is equal to 200. And so you can see I'm much more in the middle of this region where there can be significant improvement by using the linear contract over the conditional contract. And so going back to Pradeep's earlier question, the location of this line really depends on the H as well as the F theta. And so we were really only able to do this exercise for US, but we think that more empirical sort of calibration of these parameters can help us understand which of these regimes we're likely to be in. So to summarize what we've done today, we took a contract design approach to PES, and we found that the commonly used conditional contracts can perform arbitrarily poorly. And the reason here is that conditionality is too stringent and it leads to low take-up of the program. Basically, none of the agents opt in. And we find that this is particularly true when the relative environmental value is low or intermediate. So we say, maybe we can use a different kind of contract. The optimal contract is likely too complicated to be implemented, but we can use a linear contract that just relaxes the conditionality requirement, but still pays a proportional price. And we find that a distribution-free price can guarantee half the optimal payoff. And we can do better, of course, if we're allowed to calibrate that price according to our knowledge of the distribution. And then we found using a numerical study that the gaps are most pronounced when deforestation risk is high, and developing countries have this combination of high deforestation risk and low or intermediate relative environmental value. That means that they can likely benefit from relaxing conditionality. So this is just an overview of sort of the main point of the paper. In the paper, we also consider some extensions. We look at these conditional linear contracts, which I mentioned, where the linear payments are conditional on conserving at least some threshold amount. And obviously those can improve, but we also look at the approximation factor relative to that threshold. And we also look at other conservation cost functions. So in the presentation today, for simplicity, we just looked at this quadratic conservation cost function. And so if we have other conservation cost functions, you can bound, instead of a 2 or a half, you get something that depends on the curvature and slope of that function. Moving ahead, we think there are a lot of interesting things still to explore in this space. So as I mentioned, the assumption that forest utility from forest is linear is a non-trivial one. And in a lot of these programs, there are a number of different aims on top of carbon sequestration. So thinking about biodiversity, for those kinds of settings, we really want to think about complementarity of forests. And then also, particularly for the smallholder setting, it's also important to think about stochastic costs, where the smallholder farmers have these cost shocks depending on sort of their environment, their family situation that year, as well as thinking about, well, what about contracts that last over several years? How can we think about robust dynamic contracting and how that can help in PES? As I mentioned earlier, a lot of thinking about which regime we're in depends on being able to estimate the F theta and the H, so the baseline conservation and the conservation cost. And so really, I think a lot more empirical work could significantly improve our understanding of why different programs are performing well or not as well. And then a final direction I think could be really interesting is specifically in the smallholder setting. Often the contract is not just with one particular smallholder, but a whole group, say the whole village or the group of people who collectively own a particular area of land. And so thinking about group contracting and contracts with externalities would also be a really interesting approach here. So I think I'm at time, so I will end, and thank you so much to the organizers and session chairs.